Hi everybody, my name is Umit Akgun from Stony Brook University. I'm going to talk about our work Re-Animator system called tracing and replaying infrastructure. This work has been done in collaboration with Harvard College. Before we get into details, I would like to discuss why we need powerful system called tracing and replaying tools. Modern applications and operating systems are getting more and more complicated every day. As a result, analyzing and evaluating how applications interact with the operating system and hardware becomes very difficult. If we have a powerful system called tracing and replaying tools, even without having the actual application's binaries and data, we can still do the realistic benchmarking on different hardware and software stack and find performance bottlenecks. Let's talk about what is missing in the current system called tracing and replaying tools. One of the most important things is the lack of data capturing capabilities. The reason why data capturing is crucial because modern storage software has capabilities like compression, deduplication, and bit pattern elimination. To replicate the exact behavior of the applications, we need to have that data capturing abilities. You may have questions here about the security. You can find more details in the paper how we address these concerns. Another challenge is having high overhead, which prevents tools from capturing real application behavior. And most of the time, system call tracing tools do not come with replayer and don't have the standard tracing format. That is why we designed the Re-Animator tool to solve all these problems. Re-Animator can capture and replay 70 system calls which are related to file system and storage. Re-Animator also comes with a replayer. In replayer, we focus on mainly preserving before-after timing relations and the logical file system state correctness. Our other primary design goals are minimizing overhead and fidelity. Even though we capture system call buffers and collect hundreds of gigs, the Re-Animator overhead can be as low as 5%. But there is a balance problem here. Modern system call capturing tools prioritize adding less overhead over fidelity. That's why we implemented the blocking mode option. Re-Animator is designed for capturing traces for long-running applications. For example, servers that run more than an hour. Our replayer can be configured to run verification mode to check whether the correctness of the correctness of the return values and the buffer contents. In this way, we want to achieve logical file system state verification. But there are some limitations. We will talk about those limitations in the later slides. Re-Animator uses DataSeries, which provides tools for offline data analysis and format conversion capabilities. We designed the Re-Animator so that it is effortless to extend Re-Animator's both capturing and replaying abilities. The first design goal that we will discuss is fidelity by explaining how Re-Animator LTTNG integration works. The Re-Animator tracer is orchestration tool, is responsible for both configuration for tracing and executing the traced applications. For configuration part contains configuring Re-Animator for following up fork processes, setting the number of subbuffers, and enabling trace points. After that, the traced application starts running and issues system calls. Re-Animator collects data buffers and creates a record for them, which contains record ID. Record ID is the same record ID in the metadata records. Captured buffers are collected into a file with our own format, and metadata records collected into the CTF file. These two files will be processed together by Babel trace after tracing ends as an offline process. The second design goal that we will be discussing is low overhead. And in this design goal, we will be discussing on how Re-Animator collects data buffers. To reduce the overhead of data buffer collection, we offload this process to multiple threads. Whenever the Re-Animator collects data buffer, it will be assigned to one work queue thread, which is responsible for writing the data buffer to the captured buffers file. We configured our system that if there is no work queue thread is available, it stops the execution and throttles the system in order to trace the application without losing any data. We have looked at the system call capturing part. Let's take a look at the replayer design also. Re-Animator supports multi-process and multi-threaded application tracing and replay. To replay multi-process applications correctly, we simulate file descriptor tables in user space. Our verification process happens on the fly while the system code replaying happens, and it checks return values and buffer content. But a verification might add an extra overhead to replaying process. That's why the default configuration of the replayer runs without verification. As we discussed before, there are some limitations to reproduce a logical file system state. It's very hard to reproduce A time, M time, C time for the files, or almost impossible for procfs operations. To make our replayer scalable, we have to reduce the overhead of multi-threading management in the replayer. So that's why we use log-free data structures. We will focus on only level DB macro benchmarks in evaluation because of the limited time that we have. We captured the level DB read random benchmark on a machine that is configured to have only 4 GB memory. The reason why we configured the 4 GB because we want the system to become IO bound when it works with the larger database sizes than the memory size. Y-axis represents milliseconds per operation, and x-axis shows the different database size configurations for the level DB benchmark, which is mmap disabled. As you can see, the difference between 4 GB and 8 GB vanilla benchmarks, when level DB database doesn't fit into memory, benchmark becomes IO bound, and execution time for each transaction takes longer. You can see at least at 10x. When the applications are not IO bound, database transactions happen faster, and it gives the tracing system less time to catch up. That's why we see huge tracing overheads in the case of 4 GB. But when the applications become IO bound, like 8 GB case, we see only 9% tracing overhead. For the Re-Animator's fidelity and accuracy, we implemented blocking mode for our LTTNG backend. In this slide, we show tracing DB bench with the different subbuffer sizes and how much overhead blocking mode is introduced to execution. If the subbuffers are full, the blocking mode forces the tracing system to yield the threads that are responsible for draining subbuffers. We run level DB bench with a default configuration, which is 100 MB database in this experiment. We can clearly see the correlation between the number of yields and the overhead of Re-Animator tracing. If we put more memory pressure on the tracing system by providing less memory for the subbuffers, the Re-Animator throttles the application more, and as a result, we see higher overhead numbers. In this experiment, we would like to evaluate how the overhead of tracing with Re-Animator changes with the tracing devices, mmap operations, and data capturing. The left-hand side of the graph shows mmap-enabled version of level DB results, and the right-hand side of the is mmap-disabled versions. Hatched patterns that you see in the graph denote that the data capturing is enabled, and we can see the device information in the experiment names. So there are 3 main takeaways from these experiments. First, if the data capturing is enabled, having a faster capturing device reduces the overhead of Re-Animator tracing. Second, if the data capturing is disabled, there is a negligible overhead difference between faster and slower devices. And third, once we enable the mmap operations for level DB, Re-Animator tracing performs better because each operation becomes page-wise reading and writing. But in the case of mmap disabled, DB transactions happens in finer granularity. In conclusion, the main takeaway from this presentation, our main difference is capturing all information, including data buffers, in order to reproduce the original application exactly. While achieving this goal, we also keep the overheads low with high fidelity and accuracy. We tested Re-Animator with long-running I/O workloads. We showed how scalable the Re-Animator is. And here is the end of my presentation. Thank you so much for listening. We are releasing the Re-Animator source code. Please check out Stony Brook File System and Storage Lab GitHub webpage.
So I've got a question. That is, it seems very interesting that the overhead drops a lot when you have an I/O bound application, which kind of seems counterintuitive. If it were I/O bound, wouldn't it take more time to process all the I/Os as opposed to CPU bound, where you're busy doing other things? Why is it, do you think, that you actually have lower overhead for I/O bound applications?
So the reason why the I/O bound application, the overhead is lower, because once the application becomes I/O bounded, there will be time to catch up for tracing system, because there will be an empty time between the I/O operations. And then we are not capturing on the same device, so that comes with I/O parallelism. So yeah, we can do, yeah.
So the key thing here is that I/O bound has a much lower overhead, in part because you're actually able to leverage multiple devices. So that's the key assumption here, is that you have one device that you're working on and a second device that's separate that you're tracing to. And because I/O bound applications aren't CPU bound, you can use the CPU time to catch up. Is that?
Yeah. No, the tracing system also uses the CPU. So if you're so if you're not I/O bounded, so we throttle the systems. That is the thing.
Right. No, that's fair. So I think that was an unstated assumption, or at least I missed it in the paper.
Yeah.
Maybe my fault, that you were tracing on a separate I/O device, which meant that you got to overlap the two of them.
Yeah. Yeah. There is a separate. So the tracing device. So the captured buffers are going to the separate device. Yes.
Got it. Okay. That makes very good sense. Okay.
Yep.
Go ahead. Do we have other questions on this? If not, I'll go ahead and ask another question. I'd rather other people ask questions, though. So please, other folks want to ask questions? Okay. So Danny has a good question. Did you capture interesting traces with your tool that are worth sharing?
That is actually the one of the other main goal for the this project. So you can find a lot of block traces stuff, right? So if you go to the senior web page or other places, you can get block traces, because it's pretty nice. It's really it's also very anonymous too. So those are just block indexes. So the issue with this, we would like to actually get some traces and release them. That is the main issue. So that is the main goal, but we have to anonymize that. So if you want to get realistic so if you want to get the realistic system call traces from the industrial applications, from actual application, we have to anonymize that. And then if we do it, yeah, we will release that too. But we captured mainly for the database applications right now. Okay. It's like level DB and things like that. Yeah.
Okay. So I do have another question, since I'm not sure that I see, wait, here we go. Michael Factor asks, how applicable would these ideas be to collecting other classes of system calls, such as networking?
That's a good question, actually. So we are able to capture networking system calls, but we cannot replay. So that's the issue. So we can actually capture them. So we can get the data. We can get all the data that like a send or receive or something like that. So there is no issue for that. But the issue is it's not replayable. So we can only simulate those things. But it is applicable. Yeah, we can capture as many system calls as we can. Okay, good. It's over 100, I guess, 90 something. Yeah.
All right. So Rahul asks, how about deduplication-based storage?
Yes. What do you mean exactly? What happens to compressibility issue? So actually the main thing is the application. So because this is the system call level, so we see all system call transactions. The application happens in the block layer, or maybe the file system layer. So it's supposed to be lower than this. Yeah.
Okay.
Yeah.
So I've got one final question, and that is, with mmap, what you're doing, I think, is you're saying, well, when we write back the cached file, in other words, when we write back the cached memory page, that's when we record the trace. But the thing is that that now includes the write back policy, in other words, the timing of the write back and things like that, as part of the trace, which might make it a little more difficult to modify that kind of behavior. In other words, use that trace to save. What about if we had a better caching write back algorithm or something like that? Is there any, I mean, and there's obviously no way to capture every memory write, because that's not going to work. So how would that interact with replay and experimentation?
So, for the mmap, the granularity of the correct, so how can I explain that? So the granularity of the mmap is the page, right? So once you read the file page, put into the memory, we capture that. And then once you write back, we capture that. So we don't have any other transactions between those because those are all memory accesses. We have no idea actually what is going on or what are you changing or what things like that. But you're right. It depends your page case size. It depends on many other things. That once, so when you are going to write back to page to the disk, that is correct. So, but that's actually what we want to capture. So we want to capture on the system, and then we would like to replay exactly that system. So that means that if you are asking, or if I want to do the tracing in the 4 GB, but want to replay in the 8 GB machine, yeah, there will be some differences. You are right.
Right, or I want to capture it in 4 GB, but I have a different write-back policy, things like that. That's
yes.
what I was asking about.
Yes, yes,
that is true. You can't change the write-back policy because it records when you wrote back, but now that's kind of assuming the algorithm that was using already.
Yes, exactly. Yes, that is kind of the part of the trick, actually.
If you write something, right? If you rewrite it to a cache, it can record, I wrote it to the cache, and then not worry about when it was flushed to disk. But if you're talking about mmap, you can't do that, and that's why I was asking about that.
Yep.
Okay, good.